Morning. So it's time for us to get started. On Monday, we started our discussion on formulation of linear programming problems, and we went through some applications in terms of the applications related to what are practical problems in which you can apply linear programming. Formulation in terms of production planning examples, the scheduling examples, and we also did the diet problem. One thing that you can get from those problems is that there are some similarities in terms of how the decision variables are formulated, how the objective function is constructed using those decision variables, and how the constraints are looking at making sure that you take into consideration your capacity limitations for the different applications. So the last few examples that we discussed, sorry, I'm going through all of them quickly, were in terms of scheduling. So we did the production planning, and then we did the manpower planning, which is what I'm referring to as the scheduling problems. And we discussed these two examples that were similar in the sense of knowing what is the demand and then try to schedule resources around that demand with the goal of minimizing or using the minimum number of resources possible. So we did that for the bus scheduling problem. We look at the number of buses that were needed throughout the day. In this case, we had an 8-hour shift because buses needed to run for 8 hours and then they needed some maintenance. So we knew from the beginning that these buses were going to run for 8 successive hours a day only. But our demand is changing every 4 hours. So the idea was to look at the decisions of how many buses are needed per shift, 8-hour shifts, knowing that the demand will be changing every 4 hours. So we were defining each decision variable in terms of when the shift will get started. So we were thinking, or we were formulating the problem, looking at these time intervals, the beginning of each time interval, and defining a shift starting at 12 a.m., a shift starting at 4 a.m., 8 a.m., every 4 hours until midnight. So in this case, because we define this every 8 hours, we will end up with 6 decision variables representing the beginning of each shift. So our decision variables were in terms of the number of buses needed in shift I, and we look at the different beginnings here. So first shift will last for 8 hours. Second shift, represented by X2, lasts 8 hours, and so on, until we get to the last decision variable, X6, which starts at 8 p.m. and goes until 4 a.m. And then the cycle is repeated, so we don't have to define any other variable at this point. So the question now is, using these decisions that we are trying to make, finding an objective function and finding the constraints for this problem, So the objective function was to minimize the summation of the total of buses. So we want to make sure that we have the minimum number of buses. And the constraints were defined in terms of the different shifts. So number of buses in operation, and then when. So that's what we needed to go back here, looking at each 4-hour time period, which decision variables were addressing that time period. So for example, from 12 to 4 a.m., decision variables X1 and X6 will be taking care of that 4-hour time period. And then from 4 a.m. to 8 a.m., we have X2 and we have X1 and so on. So that's how we come up with this number of buses in operation per 4-hour time period. So from 12 a.m. to 4 a.m., X1 plus X6 and so on. And using that information, we can come up with the constraints. So we know that this number from 4 a.m., from 12 a.m. to 4 a.m., we need at least 4 buses. So the summation of X1 plus X6 has to be greater or equal to 4. And for the time period between 4 a.m. to 8 a.m., we need at least 8 buses. So the summation of X1 plus X2 has to be greater or equal to 8. Same thing from 8 a.m. to 12 p.m. We need at least 10 buses. So we want the summation of X2 plus X3 being greater or equal to 10. And the process is repeated until we get to the last time period for the day, which is 8 p.m. to 12 a.m. And we need at least 4 buses. So X5 plus X6 has to be greater or equal to 4. So that's in terms of the bus scheduling problem. And then we saw how the model looked like after setting up the objective function, the constraints, and the decision variables. So after this problem, this is one of the problems that we discussed on Monday. We look at another application, but we were able to see that even though it was a different application, the model was quite similar. The idea, and that was the idea. Now, in terms of looking at buses, we were looking at the number of people required in the post office every day. And we were looking at trying to come up with a minimum number of employees that we needed to hire for the post office. And we saw that depending on the day, we have a different required number of people. So Monday 17, Tuesday 13, Wednesday 15, and so on. So now the time period is expressed in terms of the day. Previously, in the previous example, was expressed in terms of 4-hour periods. Now it is expressed in terms of a single day. And the number of people required is same as the number of buses required per time period. So it's the same problem in some sense. Now we have, instead of looking at the entire shift of 8 hours for the buses, we have a requirement that employees will work at least, but must work 5 consecutive days. So in the previous example, we wanted to run the buses for 8 hours. Now we want to have people working 5 days in a row. So again, different applications, but same principle in terms of the formulation of the problem. The post office wants to meet its daily requirements using only full-time employees. So we wanted to formulate this problem to find out to minimize the number of full-time employees who must be hired. So the question to be answered, same thing, how many employees begin to work on each day? In the previous example, how many buses we needed to at the beginning of each shift. Time period is, the index is used to define the time period, and the decision variables is the number of employees beginning work on day I. So the objective function again is to minimize the total number of employees. So that would be the number of people working or starting to work on Monday plus the number of people starting to work on Tuesday and so on until Sunday. So the objective function again is the summation of those decision variables from X1 to X7. And then the constraints is where we have to spend a little more time trying to come up with the with the information that we need to set up the constraints. So as I explained on Monday, if you're able to develop a table or a figure like this one, in which you set up the days and the days for as a column and the days as a row, and then you start mapping how long will each shift will go. So for example, if you start on Sunday and you work 5 days in a row, you're gonna stop on Thursday. If you start on Monday, you're gonna stop on Friday. If you start on Tuesday, you're gonna stop on Saturday, and so on. So if you start on, say here, you don't see the whole thing. So if you start on Saturday, you see that you're gonna work Sunday, Monday, Tuesday, Wednesday, and Saturday. So you are not gonna work on Thursdays and Friday. So this information is gonna help you set up the constraints. So for example, if you need 17 people on Mondays, you know that you're gonna cover those 17 people with the personnel who started working on Sunday, started working on Monday, started working on Thursday, Friday, and Saturday. Because those are the ones that are gonna be working on Monday. So the summation of those decision variables, x1, x4, x5, x6, and x7 has to be greater or equal to 17. The same process is repeated for every day. So if you wanna know, for example, for Sunday, who's gonna be working on Sunday? The people who started working on Sunday, x7. The people who started working on Wednesday, Thursday, Friday, and Saturday. So x3, x4, x5, and x6, and x7. So when you look at that constraint, which is what we have here for Sunday, you see x3, x4, x5, x6 plus x7. That will be greater or equal to 11. So again, same idea in terms of scheduling. Application is different, but you end up with a similar format in terms of your setup. And the idea again with this lecture is that you start familiarizing with these different applications. And when you are faced with a problem, you can refer to this library of problems. Say, okay, this looks like a scheduling problem. This looks like a production planning problem. And then when you try to formulate that problem, you have these guidelines to say, okay, this is how we formulate using this format. And I can follow that format to formulate this new problem. So that being said, I want you to try that. So I have this problem. This is gonna be your lab for today. I want you to try to formulate this problem in a piece of paper. And this is gonna be due tonight at 11:59. And it's a scheduling problem. But this one has some additional challenge in it. And I want to see how you come up with a way to address that additional challenge. So I'm going to give you some time to work on this, and then we will go discuss the solution. So let's try that. 3 more minutes. you 1 minute and let's talk about this. Okay, so let's discuss this problem. So I already wrote some of the information that was given in the problem. We have 4 different shifts. These are 6-hour shifts, and I have listed them using numbers. So the first one from 12 a.m. to 6 a.m. The second one from 6 a.m. to 12 p.m. Third one from 12 p.m. to 6 p.m. And then the last one, number 4, 6 p.m. to 12 a.m. And we also have some data in terms of how many workers are needed per shift. So as you can see, shift 1 requires 15, shift 2, 5, shift 3, 12, and shift 4 requires 6 workers. So the additional constraint or limitation for this problem is that workers can work 2 shifts in a row or consecutive shifts. And when that's the case, they are paid $12 an hour. But if the workers end up working 2 shifts, they have to pick up 2 shifts, and they are not consecutive, then they are paid $80 an hour. So the challenge for this problem is to see how to model these 2 different options, like how to set up the problem to consider the workers that are working consecutive shifts and workers that are working shifts that are not consecutive. So as a modeling technique, we can define index for our decision variables. And in this problem, we can formulate the decision variables using, instead of just 1 index, 2 indexes that can represent each shift. So we can use I to represent the first shift and J the second shift. So what is the idea? The idea is that we can find all the possible combinations with total number of 4s that will satisfy the combinations that are needed for these different shifts. So for example, if we're thinking about consecutive shifts, we're going to have a limited number of options. There could be shift 1 and 2, 2 and 3, 4 and 1, and those are going to be all the options, because after 4-1, you go back to 1, 2, 3, 3, 4, and so on. So you're going to end up having 1, 2, 3, 4, 4 different consecutive shifts. Those are again shifts. So in terms of consecutive shifts, we have 1, 2, 2, 3, 3, 4, and 4, 1. This could be also 1, 4. It's the same thing. And so after that, then you go back to 1, 2, 2, 3. So all possible combinations for consecutive shifts are 1, 2, 2, 3, 3, 4, and 1, 4. That's all you can do with these 4 shifts. And we can do the same thing with the non-consecutive shifts. So how can you represent those using these indexes? So for the non-consecutive shifts, you can have 1, 3, right? 1, 3. And what is the other option? 2, 4. 2, 4. Other than that, you go back to the same list. So you only have 2 options here. You start in shift 1, you skip 2, go to 3, or you're starting 2, skip 3, go to 4. If you're starting 3, you are going back to the same process. 3, you skip 4, and then you go to 1. So you end up working 1 and 3 anyways. Okay. So in terms of non-consecutive shifts, we have these two other options, 1, 3, and 2, 4. So my decision variables are going to be using this information, these indexes. Okay, so my decision variable can be defined in terms of xij, which is the number of workers working shift 1 for I and j. So x12, x23, x34, x41, x13, and x24. Those are going to be my decision variables. My objective function is going to use the information about the cost. So if you are working consecutive shifts, then you're working 12 hours and you're paid $12 an hour. So 12 times 12 is 144. So these people at the end of the day will earn $144. And those are for consecutive shifts. So 1, 2, plus x2, 3, x3, 4, plus x1, 4. And then we have the other option, which is working non-consecutive shifts. And these are paid $18 an hour. So 18 times 12 equals 216. And this is for the decision variables in which you have non-consecutive shifts. So that will be x13, x24. So that is the function. And obviously, what you're trying to do is to minimize that function. So you want to minimize the objective function, which is the summation of the number of workers that are going to be earning $144 at the end of the day, and the workers that are going to earn $216 at the end of the day. So that's the objective function. Now we have to formulate the constraints. And the constraints are going to use the information from here, workers that are needed per shift. So we have a constraint for each shift. So this is for shift 1, shift 2, shift 3, and shift 4. So for shift 1, we want to make sure that we have at least 15. For shift 2, we want to make sure that we have at least 5. For shift 3, we want to make sure that we have at least 12. And for shift 4, we have at least 6. So the summation that is going to happen on the left side has to make the right-hand side, meet that right-hand side at least this much, right? At least these many workers. So for shift one, I'm going to look for those decision variables that have an index equal to 1, because that means that that decision variable is representing number of workers for that shift. So for instance, if I look at this list, I have X12, I have X14, and I have X13. Those three are accounting for workers that are going to be working shift one. So my left-hand side for shift one, X12 plus X13, X14. So X12 represents the workers starting in shift one and working shift two, consecutive shifts. X13 are those that are starting on one, skipping one, and then working on shift three. And X14 represent those that are working shift 4 and 1. Following the same process, I can do shift 2. So shift 2 is also going to have X12, X23, and X24. Shift 3 will have those decision variables that are accounting for shift 3. So X13, X23, and X34. And finally, shift 4, we have the decision variables that have an index 4, so X14 plus X24 plus X34. And I want all my decision variables to be greater or equal to 0. And that's the formulation. So as you can see, this has an additional challenge. That challenge is having workers skipping or working non-consecutive shifts. And the way we handle that is by defining a second index that is going to be attached to that decision variable. It's going to allow us to look at the different combinations of shifts that can be applied to this problem. Questions? Yes, you can. The question is not, the problem is not forcing you to a minimum number of workers. So can we just assign people to non-consecutive shifts? Oh no, it's more expensive actually. So the question, yes. So I see what you're saying. So it's less expensive to have everyone working consecutive shifts. But if you see the demand, it's changing, and the number of workers needed is changing, and you can see how it goes from 15 to 5, 12 to 6. So if you schedule 15, all of them at the beginning of shift 1, and they work shift 3, then you will have more people than what you need in shift 2 and 4. So you will end up spending more money because these resources are idle for those shifts. Yeah, but that's a good observation. Good point. Any other question? Good. So I have some additional problems to discuss today, and this is going to be the rest of the lecture. So we're going to look at other applications. Again, practical problems as industrial engineers are not just constrained to working in a manufacturing facility. We are right now needed in multiple or different applications, different organizations, service, manufacturing, electrical, healthcare. So our skills can translate to many, many different applications. So one of those is planning at the government level, not only, I mean, as we saw in the transportation, and I mentioned that in the last lecture, I was able to work in a transportation agency when I was an undergrad, as an intern. So again, we have many different options in terms of work. So one of those applications is urban development planning. And the idea here is to plan for the reconstruction of a specific area in a city. And this city is faced with a severe budget shortage. The city council votes to improve the tax base by condemning an inner city housing area and replacing it with a modern development. The project involves two phases: demolishing substandard houses to provide land for the new development and building the new development. So if you live in this area, you have seen how that's been happening, especially in Austin. The areas are being demolished, and then you have all these new buildings coming up. So that's what we are trying to model here. The following is a summary of the situation. As many as 300 substandard houses can be demolished. Each house occupies a 0.25 acre lot. The cost of demolishing and condemned house is $2,000. Lot sizes for a new single, double, triple, and quadruple family homes units are 0.18, 0.28, 0.4, and 0.5 acres. Streets, open space, and utility and easement accounts for 15% of the available acreage. In the new development, the triple and quadruple units account for at least 25% of the total. Single units must be at least 20% of all units, and double units at least 10%. The tax levied per unit for single, double, triple, and quadruple units is $1,000, $1,900, $2,700, and $3,400 respectively. The construction cost per unit for single, double, triple, and quadruple family homes is $50,000, $70,000, $130,000, $160,000. And financing through a local bank is limited to $15 million. So a lot of data here, a lot of information. So costs, the income in terms of tax that you're going to receive, and financing limitations, the cost of construction. So how do we take all this information into account to make decisions of how many units of each type should be constructed to maximize the tax collection? So what are the questions to be answered? How many units of each type should be constructed? Demolished to maximize the tax collection. And in this problem, we're going to have I representing the type of home, and XI the number of units of type of home I. So as you saw, there are 4 different types. So again, how many units of each type should be constructed to maximize the tax collection? The variables of the model are the number of units to be constructed of each type of housing, and the number of houses must be demolished to make room for the new development. Okay, so we're going to try to find out, okay, I'm going to demolish this many houses to build these new ones. So we're going to have X1, X2 up to X5. X1 through X4 are representing the new construction in terms of the number of quantity, I will say, of space. And then X5 is the number of old homes to be demolished. So we want to maximize the total tax collection from all 4 types of homes. So the objective function is, this is what we are going to collect if we build single, double, triple, and quadruple. So we want to maximize this collection. So yes. Yes, so X5 is going to be, I'm going to show you that in a minute. So we have, where is it? We have a cost associated with demolishing each house. So we're going to apply that to the objective function now. So that's why we need to account for the number of houses that are going to demolish. Because it's going to be, you're going to find the profit, which is going to be the collected money minus the cost of building the, oh, participants can now see your screen. What happened? Okay, so I'll fix, if you are not looking at the lab, yes, you can use the, I'm going to post it after the lecture, but the idea was that you followed the discussion and you saw the problem as we discussed we were discussing it here in class. But I'm going to open that at the end of the lecture so you can upload your answer. Okay, so going back to the discussion. X5 is the number of old homes to be demolished. So when we look at the objective function, we have the piece about the collection. And now we're going to look at yes. Yes. So you'll see how it's going to how that's going to be taken into account in a minute. So we want to maximize this tax collection, but we still have to represent the cost associated with the with demolishing those homes. So let's continue the discussion and you'll see how that's taken care of in a minute. So the first constraint is deals with the land availability. So again, there's no space now. We have to create that space by demolishing these structures. So the acreage used for new homes has to be less than or equal to the net available acreage. So this is the amount that we need per type of home. So we're going to be summing that space. And to determine the available acreage, each demolished home occupies 0.25 acre lot, thus netting 0.25 x5 acres. So whatever we have on the right-hand side, which is going to depend on the number of houses that we develop, that we demolish, has to be the left-hand side, which is this summation, has to be less than or equal to the amount of space that we are going to create. So allowing for 15% open space for street and easements to the net acreage available. So we have to accommodate this requirement for the development. So not all the space will be used for creating new homes. We have to leave some space for parks, space, open space, streets, and so on. And that's 15%. So we only have 85% available for the construction of new homes. So we're going to be multiplying that amount times this to get the resulting amount, which is 0.2125 x5. So every time you demolish a home, this is the amount of acreage that you're going to gain for homes. So the resulting constraint is going to be equal to the summation of this space that you need to build new homes, and that has to be less than or equal to the space that you're going to create by demolishing those homes, those old homes. So in order, you can reorganize this constraint. You can move this to the left side and make it less than or equal to 0, or you can just keep it like this, up to you. Or typically we want to have the decision variables all on the left side of the problem. The number of demolished homes cannot exceed 300, which can translate into x5 less than or equal to 300. And the constraints limiting the number of units of each home type. As we saw, for a number of single units, it has to be at least 20% of all units. Double units has to be at least 10%. And number of triple and quadruple has to be at least 25%. So what we are doing is, again, putting a lower bound for each one of the decision variables, saying like, okay, for X1, we have to make sure that we build this many, which is going to be 0.20 of the total number of homes. So X1 has to be at least 20% of the summation of all new homes that you're going to build. X2 has to be at least 10% of all the homes that you're going to build. And the summation of these two has to be at least 0.25 of the total of the homes that you're going to build. Keep the demolition construction costs within the allowance budget. So we now have this construction and demolition cost, and the available budget is 15 million. So we are expressing everything in terms of thousands of dollars. So that's why you see 15,000. So the cost of building these new developments per home type is, I think, 50,000, 70,000, 130,000, and 160,000. Plus the cost of demolishing these homes has to be less than or equal to the budget that we have available. So that's how we are using that information in terms of making sure that we are meeting our budget. And this is the final formulation for the renewal model. We have the maximization of the income that we're going to get from taxes. And then that's going to be subject to the limitations that we have in terms of space and the limitations that we have in terms of how many units we can build and demolish. And then we also have a limitation in terms of the budget that is available. Urban renewal model. Questions? Okay, good. Let's see what we have. Project selection, another one that is very relevant to what we do as industrial engineers. So in this one, we are looking at investments. So Star Oil Company is considering 5 different investment opportunities, and we have the cash outflows and net present value in millions are given in the table. So we have times 0, the cash outflow, time 1, the cash outflow, and the net present value for each one of these 5 investments. So this company has 40 million available for investment now at time 0. It estimates that 1 year from now, at time 1, 20 million will be available for investment. Company might purchase any fraction of the investment of each investment. In this case, the cash outflows and net present value are adjusted accordingly. So for example, if the company purchased 1/5 of the investment number 3, then a cash outflow of 1/5 times 5 equals to 1 million will be required at time 1. 1/5 share of investment 3 will yield a net present value of 3.2 million. Company wants to maximize the net present value that can be obtained by investing. So we want to formulate an LP that will help achieve this goal. Assume that any funds left over at time 0 cannot be used at time 1. So what are the questions to be answered? What fraction of each investment to purchase? So I is going to represent the type of investment that you're going to make. And then XI equals the fraction of investment of I to purchase by the company. To maximize the net present value earned from the investment, our objective function is going to maximize the summation of the net present value for each investment. Then we're going to have 3 constraints. may be expressed as follows. Constraint 1, start cannot invest more than 40 million at time 0, and start cannot invest more than 20 million at time 1. Constraint 3 is start cannot purchase more than 100% of investment. So it's just limited to what 100%. Constraint 1, so we see how much it costs to invest, right? So I have 11, 53, 5, and 5, and 29. So the summation for that has to be less than or equal to 40. So right there, you will see, oh, well, why are we considering this, right? So it's greater than 40 already. But remember, we can purchase a fraction. Okay, so even though we cannot purchase the whole thing, we can purchase a fraction, and then that will be less than or equal to 40. Constraint 2, start cannot invest more than 20 at time 1. So again, same thing here, 34, even though it's greater than 20, we can purchase a fraction of it. So constraint 3, start cannot purchase more than 100% of investment. So we want to make sure that our xi's are always less than or equal to 1. So we don't make that greater than 1. If we make xi greater or equal to 1, then we are purchasing more than 100% of the investment. So the net present value earned from investment is the summation or the maximization of the net present values. And then we have the constraint limitations in terms of how much you can invest per year. And you need to make sure that you don't go above 100% for any of the investments. So the solution of this problem is going to involve some fractional values for each investment that are going to maximize the net present value. So you will see, for example, here, this is giving you a very high net present value, but also the cost of investment is pretty high. So you get a high investment, you get a net present value that is high, but also it costs you a lot. So finding the right combination is the solution for the problem. Okay, so the last one is the blending and refining. So the reason I present this one is for those students who have interest to work for the oil companies, Chevron, Saco, and so on. So here we are looking at finding the right mixture of ingredients so we can get the products that we need as an output. So we have a company that has a capacity of 1.5 million barrels of crude oil per day. The final product from the refinery includes 3 types of unleaded gasoline with different octane numbers. We have 87, 89, and 92. The refining process has 3 stages. It has a distillation tower that produces feedstock with ON equals 82 at the rate of 0.2 barrels per barrel of crude oil. So every barrel of crude oil is transformed to 0.2 barrels of this feedstock of the ON equals 82. And we have a cracker unit that produces gasoline stock with an ON of 98 by using a portion of the feedstock produced by the distillation tower at the rate of 0.5 barrels per barrel of feedstock. Okay, so every barrel that we get from the distillation tower is transformed to 0.5 barrels of these ON equals 98. A blender unit that blends the gasoline stock from the cracker unit and feedstock from the distillation tower. The company estimates that the net profit per barrel of the 3 types of gasoline to be $6.7, $7.2, and $8.1. The input capacity of the cracker units is 200,000 barrels of feedstock a day. The demand limits for regular, premium, and super gasoline are 50,000, 30,000, and 40,000 barrels per day. So we want to develop a model for determining the optimum production schedule for the refinery. So I think I have a picture of this process that will make more sense. Let me see. Somewhere here. Okay, so yeah, I have the picture. So I will show you that in a minute. So what are the questions to be answered? How many barrels a day to produce certain type of final product? So we have these three different final products. So we have the indexes that represent the barrels a day of the input stream that are going to be transformed to a final product J. So how many barrels of input we are using to create this output, final product. Decision variables, Xij is the barrels a day of input stream I. So you see how we have different inputs, and you'll see this in the picture in a minute, to blend the final product J. So two different input streams and three different products at the end. So the variables can be defined in terms of two input streams to the blender, feedstock and cracker gasoline, and the three final products. So we go back to Xij. So using this definition, we have the daily production of regular gasoline. So regular gasoline is index J equals 1. So that's why J is equal 1 on both of these decision variables. And then we have two processes, 1 and 2, to blend the final product. So we have stream I, and for that we have streams 1 and 2, which are the feedstock and the cracker gasoline. So for daily production of premium gasoline, again, we have two inputs, 1 and 2, and the type of gasoline that you're going to produce is 2, which is the premium. So it's represented by J equals 2. So that's why J equals 2 in both of these two decision variables. And the daily production of super gasoline, same thing. I represent the process that I used to get that final product 3. So 1, 3, and 2, 3. So daily production of regular gasoline is going to come from two different processes. Daily production of premium gasoline is also coming from these two different processes, and daily production of the super gasoline is also coming from the two processes. So the maximization of the profit that we are going to get is our objective function. So we get $6.7 per regular, 7.2 per premium, and 8.10 for super premium. Okay, so this is the figure. Representation of the process. So we get the crude oil here, and we get the distillation. And for every 5 barrels of crude, we get 1 in the distillation process. And then from here, we can take this feedstock, ON82, and send it to the cracker to get it transformed to an ON98 product. And then the ratio here is every 2 barrels of ON82 that you get and you send to the cracker, you get 1 barrel of ON98. If you decide not to use the cracker and send it directly to the blender, then you get ON82 from the distillation straight to the blender. You can get a 1:1 ratio for the barrels, and here you will get an ON82 product. Okay, so the difference between this source and this source is that this one goes ON straight to the blender, and this one gives you the ON98 to the blender. So the ON98 basically is allowing you to get the super premium gasoline and so on. So now that you understand this, let's try to work with the constraints. So daily output of the blender unit, which is this one, is going to be equal to the daily production of regular gas plus the daily production of premium gas and daily production of the super gas that are going from the distillation straight to the blender, and also from the cracker to the blender. So it's going to be the summation of all the decision variables, combination of both processes go to the blender, and that's going to be the total blend barrels a day. The daily feedstock to the blender is going to be everything that goes from here to the, from here to here, from here to the feedstock directly to the blender. And that's going to be everything associated with the first process. So that's why we have X11, X12, and X13 barrels a day. And the daily cracker unit feed to the blender are those associated with the second process, which is the cracker 2.1, 2.2, and 2.3. So this is the daily cracker feed to the blender. The daily feedstock to the cracker is going to be 2 barrels per 2 barrels of distillation, right? The ratio 2 to 1. So that's why we are multiplying this 2 barrels times the total that is going to be produced. And the daily crude oil used in the refinery is going to be 5 crude oil barrels to 1. So it's going to be 5 X11 plus X12 plus X13. And then for this one, you need the double, 2 times that. So that's going to be 10 times X121, X22, X23 barrels a day. So we're basically going backwards to find the requirement input for each one of the processes. So from here, we can estimate the daily crude oil supply does not exceed 1.5 million per barrels a day. So we obtain that by using this expression that is representing what's coming into the process. And that has to be less than or equal to 1.5 million. The cracker unit input capacity does not exceed 200 barrels a day. So again, we computed that daily feedstock here. There's a ratio of 2 to 1, so that's why we are multiplying times 2. So it has to be less than or equal to 200,000. And then the daily demand for regular does not exceed 50,000 barrels. So we can easily formulate that. We know how much, the decision variables that are representing the regular. So we want that to be less than 50,000. Same thing for premium. We know that decision variables X12 and X22 represent the premium final product. And we want that to be less than or equal to 30,000. And the daily demand for super does not exceed 40,000 barrels. So decision variables representing the final product, super 1, 3, 2, 3. The summation of both of them has to be less than or equal to 40,000. So this one is to compute the octane number of gasoline product is the weighted average of the octane numbers of the input stream used in the blending process and can be computed as follows. It's going to be the feedstock ON times the feedstock barrels a day plus the cracker unit times the cracker unit barrels a day. Everything divided by the total barrels day of regular gasoline. So to obtain the octane number, we have to basically input the expressions representing each one of these pieces into this equation. So you will see that is represented, again, this is the feedstock 82 times the feedstock barrels a day. X11 represents that. Cracker unit ON 98 times the cracker unit barrels a day, X2121. And this is making sure that this ON for premium is at least 87. So the summation of these two is the total. So when we can solve this or move this piece, multiply this on both sides and move it to this side of the equation. Same thing for ON premium at least 89. So we follow the same expression now for 89. We have the ON 82, ON 98, and we use the decision variables associated with the second type of gasoline, which is premium. We solve for, or we multiply X12 plus X22 on both sides. We do the same thing for using premium. Yeah, this should be regular. I'm sorry, that's a typo. This should be regular. This is premium and this is super. So same thing for Octane, for super premium is at least 92. So we look at the decision variables associated with super premium product. We do the same ratio and we solve for, or we multiply this piece on both sides. So we have the linear equation. And then finally, this is the final model. Obviously, I'm not going to ask you to formulate something like this in the exam. This is way too complicated. It will take you an hour, just this problem. But the purpose, again, of presenting this example is so for you to get familiarized with the application. Like if you end up working for something or along these lines, you can refer to this type of model to work with the problem. As I mentioned in our previous lecture, the idea after we discuss, we are going to finish this lecture today, that we're going to start discussing how to solve these type of problems by hand on Monday. And after our first exam, we're going to solve these problems that we discuss in this lecture using the computer. So you'll see how this, what are the solutions for this type of problem and how those solutions, if they make sense or not, and so on. Later in the semester, we're gonna deal with sensitivity analysis. Like, okay, you have this problem. Let's say you are changing this parameter. Is your solution still the same, or are you going to have to make different decisions? And then we'll continue that analysis. We're going to talk about the dual problem. So now we have this information. The dual can help us make decisions from a financial point of view. Like if you increase this resource, how much of an increase in your income you will obtain, and so on. So we have a lot of information, a lot of skills that you're going to develop, but everything starts from here. You need to understand how to formulate these problems efficiently so you can move forward into developing a solution and make recommendations. Okay, so that's all I have for today. I'm going to open the lab right now after I stop the recording. So look for the lab assignment so you can upload your solution. Okay, so I'll see you on Monday.